London, 1884. The air trembled with the constant hum of a city being reshaped by steel, steam, and ambition. In the great industrial age, where nations rose and fell on the power of their machines, one young engineer quietly prepared to uproot everything humanity believed about propulsion. His name was Sir Charles Parsons, and almost no one understood yet that he was about to ignite a revolution that would change the future of war. Parsons did not come from poverty, nor from obscurity. He was born into sight of a family of scholars and inventors, raised in a home where scientific curiosity was not a hobby. It was a requirement. From the moment he stepped into the workshops of his youth, he saw machines differently. Others saw gears, wheels, and pistons. Parsons saw potential. Energy trapped inside metal, waiting for the right mind to unlock it. He trained at Cambridge, where precision was not an ideal, but a discipline. He studied mathematics, engineering, and thermodynamics with an intensity that unsettled even his professors. Where most students executed equations, Parsons interrogated them. Where others memorized theories, he challenged them. It was this unusual mixture of discipline and rebellion that shaped his future. He would follow the rules only long enough to understand how to break them for something better. By the time he entered the world of industrial engineering, steam engines ruled everything. They powered factories, locomotives, ships, and empires. But to Parsons, these engines looked clumsy, brute force machines that wasted most of the energy they consumed. The problem was simple. Steam engines pushed and pulled in a violent cycle, constantly fighting friction and inefficiency. Parsons asked a radical question: why not let steam spin instead of push? This idea, simple on the surface, would become the foundation of the modern world. In his small workshop, hidden from the noise of London, Parsons began constructing the prototype of a device almost no one believed could work. A machine where steam flowed through carefully crafted blades, turning a shaft in a smooth, continuous, incredibly efficient rotation. If successful, it would produce far more power, with far less fuel, at far greater speeds. This was the birth of the steam turbine. The invention that would eventually power destroyers, cruisers, battleships, and the industrial heart of the 20th century. But in 1884, it was just an idea, and most engineers dismissed it as impossible. Parsons built the first turbine with his own hands. It was small, compact, almost delicate compared to the monstrous steam engines dominating British factories. When he first tested it, the machine spun so fast it nearly tore itself apart. Engineers whispered that it was dangerous, untested, unpredictable. They were right. Parsons had underestimated not the idea, but the sheer violence of the power he had unlocked. Instead of abandoning the project, he refined it. Thicker blades, better, alloys, new geometry. Every test failure was fuel for a new breakthrough. Then came the moment that would define the rest of his life. In front of a small group of industrial investors, men who doubted him but were curious enough to watch a demonstration, Parsons activated his improved turbine. The machine spun with unprecedented smoothness, its rotation measured not in hundreds, but tens of thousands of revolutions per minute. Noise dropped, vibration vanished, efficiency soared. For the first time in history, a machine extracted the true, unrestrained power of steam. If the industrial world of the 19th century was built on steam engines, the 20th century would be built on turbines. Parsons saw it instantly. The investors did not. They congratulated him politely, then dismissed the demonstration as interesting but impractical. It was the classic reaction of men too comfortable to recognize revolution. But Parsons had one thing they didn't: vision. He began imagining ships propelled faster than any engine could ever push them, warships that could outrun torpedoes, destroyers that could circle an enemy fleet before they even fired a shot, power stations generating electricity not for factories but for entire nations, machines that no piston-driven engine could ever dream of matching. He knew the turbine was not an invention. It was an era waiting to be born. Parsons founded his own company to avoid the bureaucratic chains of traditional industry. He recruited craftsmen, machinists, and young engineers who believed in progress, not tradition. The early years were brutal. Money short, critics loud, failures frequent. But the machines got faster, stronger, more reliable. And for the first time, the British Empire began to notice. Because an engineer with a turbine was one thing, but an engineer who could power warships, that was something else entirely. The Admiralty watched him closely. Naval power was the pride of Britain, yet its ships were slow, heavy, and vulnerable. Parsons was offering a breakthrough that bordered on impossible: speed, delivered by machines lighter, stronger, and more efficient than anything the Victorian world had ever known. And then, in a moment the newspapers would later describe as the shock that woke an empire, Parsons unveiled a demonstration that would shatter every doubt about his invention and force the world to take him seriously. But was the world ready for the speed and the danger of what he had created? How far would Parsons go to prove that his turbine was not just innovation, but destiny? By 1897, Parsons had refined his steam turbine into a machine far more powerful than anything his early critics imagined. Factories were beginning to adopt it. Power stations quietly transitioned from piston engines to turbine-driven generators. But Parsons knew that none of this was enough. The industrial world could ignore him forever, unless he attacked the problem from an angle no one could overlook. And in the late 19th century, there was only one arena where innovation could stun an entire nation at once: the Royal Navy. For centuries, naval supremacy defined Britain's identity. Battleships were national symbols, monuments of iron and steam. Admirals trusted only heavy engines with massive pistons and enormous boilers. The idea that a fragile turbine could replace them was treated as fantasy. Parsons understood something they didn't. Naval power was no longer about weight. It was about speed. The turbine could deliver that speed in ways no piston ever could. But convincing the Admiralty through reports or diagrams would never work. They needed to see it. They needed humiliation so undeniable that the old ways would crumble. So Parsons prepared something bold. He built a ship. It was small, narrow, and unconventional, nothing like the hulking battleships that dominated the seas. He named it Turbinia, a slender white vessel powered by a turbine that produced unimaginable rotational speed. The ship sliced through water with almost zero vibration, its propellers carving the sea like knives. For months, Parsons tested the Turbinia in secret, pushing it harder, faster, refining the blade shapes, tuning the turbine stages. Each test confirmed the same truth. The turbine wasn't just better, it was superior on every measurable axis. Then came the moment that would rewrite naval engineering history. The Royal Navy planned a grand fleet review at the Diamond Jubilee of Queen Victoria, a spectacle attended by royalty, politicians, admirals, reporters, and foreign observers. Warships from across the empire lined the coast, each displaying the pinnacle of British engineering. Parsons knew this was his moment. On June 26, 1897, as battleships showcased their firepower and cruisers displayed their coordinated manoeuvres, a small unknown vessel suddenly appeared at the edge of the formation. Witnesses saw a thin white shape emerging from the mist. Then, without warning, it accelerated, not gradually, but explosively, cutting across the bow waves of the largest ships in the world. The Turbinia tore through the review, weaving between cruisers and destroyers at a speed that left spectators speechless. Naval officers shouted in disbelief. Some believed they were witnessing an accident. Others thought the vessel was out of control. But the truth quickly became impossible to ignore. The Turbinia was travelling twice as fast as any ship in the Royal Navy. While Britain's best warships struggled to reach 20 knots, Parsons' vessel reached 34 knots, its hull slicing through the sea as if propelled by invisible forces. Admirals on nearby decks watched in silent shock. The public gasped. Newspapers described it as a knife cutting water. Photographers struggled to capture it. The ship outran their lenses. The Turbinia didn't just demonstrate speed. It delivered a public humiliation so complete that the Admiralty had no choice but to react. Britain had just been outclassed by a civilian engineer. Overnight, everything changed. The Admiralty requested meetings. Naval architects demanded technical documents. Parsons suddenly held the key to the future of naval warfare. Within months, Britain committed to building turbine-powered destroyers, then cruisers, then dreadnoughts. The world followed. By the start of the 20th century, the turbine had ended the age of pistons. It became the beating heart of modern naval power. And it all began because Parsons dared to embarrass the British Empire in front of itself. As orders flooded into his workshop, Parsons expanded rapidly. His turbines grew massive, designed not just for speed, but endurance and wartime reliability. He pushed materials science forward, demanding new alloys that could withstand temperatures and pressures unheard of in Victorian industry. Factories were retooled to meet his demands. Entire supply chains reorganized to support the new naval standard. The turbine was no longer an invention, it was a strategic asset. But this transformation carried consequences. War planners realized that turbine-powered ships were not simply faster, they were now essential. Speed meant the power to intercept, escape, flank, and strike. Battleships equipped with Parsons turbines became global instruments of influence. Destroyers powered by his machines hunted submarines and protected convoys. His technology reshaped naval warfare so thoroughly that no fleet could survive without it. What began as a rebellious demonstration had become national doctrine. Yet Parsons remained strangely detached from political celebration. He wasn't interested in medals or status. He cared only about perfecting his machines. While others saw military dominance, Parsons saw engineering challenges, new limits to break, new efficiencies to extract, new ways to harness steam into power. His obsession moved beyond ships into electricity, into high-capacity generators, into industrial grids that would electrify entire cities. The same turbine that powered war now powered peace, linking two worlds through a single rotating shaft. Still, even as his reputation grew, Parsons knew something others didn't. The turbine was not simply an invention of its time, it was the engine of a century. Anyone who controlled turbine power controlled speed. Anyone who controlled speed controlled strategy. This truth would shape both world wars, long after Parsons himself was gone. But with every breakthrough came a question that lingered beneath the triumph. A question that even Parsons, with all his genius, could not fully answer. Did he set humanity on a path toward progress, or toward a new kind of war built on unstoppable speed? By the early 1900s, the ripple of Parsons' invention had already turned into a global wave. After the spectacular humiliation of the Fleet Review, the world's navies realized they had only two choices: adapt or fall behind. Every major maritime nation, from Germany and the United States to Japan and Russia, began tearing apart their old propulsion systems, studying turbine dynamics, and licensing Parsons' technology. What had begun as one man's obsession now stood at the centre of a geopolitical race. The turbine was no longer just an engineering breakthrough. It had become a weapon of influence. The British Admiralty moved first. They commissioned a new class of destroyers equipped with Parsons turbines, engines capable of producing raw speed unimaginable only a decade earlier. These ships cut through the ocean like blades, outrunning torpedoes, repositioning faster, attacking from angles no admiral had trained for. The Navy quickly realised it wasn't only speed that mattered. Turbine-driven vessels were smoother, quieter, and more stable. Gunnery accuracy improved. Fuel efficiency increased. Operational range expanded. Strategy evolved because machinery evolved. By the time Britain launched HMS Dreadnought in 1906, a ship that would redefine naval warfare, the turbines were no longer optional. They were the central nervous system of naval power. Parsons' influence spread beyond the battlefield. The same turbine that brought speed to destroyers brought energy to entire cities. He recognised that the world was heading toward electrification at a scale never seen before. Factories demanded power. Rail networks demanded reliability. Cities demanded constant light. Parsons redesigned his turbines to handle extreme loads, enabling electrical stations to produce enormous amounts of power with unprecedented stability and efficiency. Turbine farms rose across Britain and Europe, massive generators driven by steam that turned electricity from a scientific curiosity into the backbone of modern civilization. His machines were everywhere, yet his name remained almost invisible. Engineers respected him, but the public knew little. Parsons preferred it that way. He avoided politics, avoided headlines, avoided the mythology that surrounded industrial giants. His legacy built itself quietly through the infrastructure he created, through ships breaking speed records, through factories operating around the clock. The world didn't celebrate Parsons, it used him, and as industrial power grew, so did military ambition. World War I erupted in 1914, and every major warship, from cruisers to dreadnoughts, relied on turbines derived from Parsons' original design. Battles unfolded with a speed and violence unmatched in history. Naval engagements became contests of acceleration, maneuverability, and endurance. The turbine didn't fire shells, but it determined how quickly a ship could aim, reload, reposition, or escape. Speed meant survival, and survival meant victory. In some sense, Parsons had militarized the element of time itself. The interwar period only amplified his impact. Nations rebuilt and rearmed, now fully aware that future conflicts would be decided by industrial capacity as much as military strategy. Power stations expanded. Naval fleets replaced outdated engines. The turbine became universal. Russia adopted it. The United States refined it. Japan perfected high-speed naval travel, using turbine-derived systems. Germany modernized its fleet with advanced multi-stage turbine configurations. By the time World War II arrived, turbines powered everything from escort destroyers, guarding convoys, to carriers projecting air power across oceans. Parsons did not live to see the full extent of his influence. He died in 1931, leaving behind a world accelerating into modernity. But his presence lingered in every engine room, every power station, every warship hull cutting through rough seas. Even aircraft carriers, the giants of naval dominance, relied on turbine propulsion systems to launch fleets of planes. In this sense, Parsons shaped the outcome of both world wars, despite never setting foot in a battlefield. Yet, there was an irony at the centre of his legacy. Parsons had devoted his life to efficiency, precision, and progress. He pursued speed not for war, but for engineering purity. Still, his invention had become one of the most powerful enablers of global conflict. Nations raced to build faster fleets because turbines allowed them to. They expanded industrial warfare because turbines fed their factories. They electrified military infrastructure because turbines made it possible. Parsons never intended to design a weapon. He intended to design a revolution. But history rarely distinguishes between the two. In the decades after his death, the turbine evolved again. New alloys, higher pressures, refined aerodynamics. Gas turbines emerged, powering not only ships but aircraft engines and early jet technologies. Nuclear submarines adopted turbines that operated silently beneath the ocean surface. Electricity grids across continents were anchored by massive rotating machines, each one a descendant of the prototype Parsons, built in a modest workshop in 1884. Even the world's most advanced warships and energy plants today, destroyers, carriers, nuclear stations, still rely on the basic principles Parsons discovered. He had not just mastered steam, he had mastered rotation. And yet, the most important question remains. Parsons changed industry, warfare, and modern civilization, but he did so without seeking power, fame, or political influence. His vision created speed, and speed reshaped the world. Some call it genius, others call it inevitability. But as turbines continue to drive the engines of nations, one question stands at the centre of his legacy. Did Parsons accelerate humanity toward progress, or toward a future where speed would forever decide? The balance between peace and war? By the final decade of his life, Sir Charles Parsons found himself surrounded not by theories or prototypes, but by an entire world built on his invention. Turbines roared in ship engine rooms, hummed in power stations, and vibrated through the steel frames of cities lit by artificial light. What began as a single rotating shaft in a small workshop had evolved into a global technological skeleton. The modern world was no longer powered by steam engines, it was powered by Parsons. In Britain, the transformation was total. Every major electrical plant relied on turbine-driven generators engineered from his original design. Coal was burned not for motion, but for rotation. Fuel feeding a machine that extracted energy with unmatched precision. Turbine stations illuminated factories, steelworks, rail networks, and entire neighbourhoods. Where the Victorian world moved slowly on pistons, the 20th century pulsed with high-speed rotation. Parsons had not just built a new engine, he had built a new rhythm for civilization. The same turbines that powered industry now reinforced military infrastructure. Naval dockyards operated around the clock. Manufacturing plants turned raw metal into warships, artillery, and aircraft components. The Royal Navy, once conservative and hesitant, now depended entirely on his machinery. Even as geopolitical tensions escalated in the 1920s and early 1930s, the ships leaving British shipyards, cruisers, destroyers, battle cruisers, all carried the invisible fingerprint of his work. They were faster, quieter, and more efficient because the turbine made them so. Yet Parsons was never seduced by the military glory that surrounded his machines. He rarely attended ceremonies, he declined political positions. He avoided the type of fame that industrialists of his era often pursued. While others sought credit, Parsons remained committed only to advancing his craft. His fascination shifted to improving turbine geometry, reducing vibrational losses, and enhancing material strength. Even late in his career, he spent long hours studying blade curvature and airflow, searching for incremental gains that others would have considered trivial. To him, the smallest fraction of efficiency was worth the effort. Perfection was a direction, not a destination. As global tensions grew, turbines became more than an engineering innovation. They became infrastructure that nations could not afford to lose. World powers raced to expand their fleets, electrify their industries, and build power networks capable of sustaining conflict. All of it required turbines. When the First World War broke out, British dreadnoughts tore through the North Sea with turbine-driven speed. Destroyers chased U-boats across the Atlantic. The turbine's quiet efficiency allowed warships to reposition without the deafening mechanical chaos of older engines. Speed meant survival, and survival altered strategy. Parsons, watching from a distance, understood the gravity of this change. His invention had evolved into a strategic asset that shaped naval doctrine, industrial output, and national security. A machine he created for efficiency had become essential for warfare. Yet, he never expressed regret. For him, technology was neutral. Only its use determined its moral weight. But the world around him was no longer neutral. Nations with turbines accelerated. Nations without them fell behind. In the final years before his death, Parsons turned his attention toward aviation and high-speed transport. He saw clearly that turbines were not limited to ships and power stations. Their potential extended into the skies. In the 1920s, he experimented with early gas turbine concepts, anticipating the engines that would later power jet aircraft. Once again, he saw a future most people couldn't imagine, and once again, the world would prove him right. Although he did not live to see turbine-powered aircraft dominate the skies of World War II, the basic principles he developed formed the foundation for jet propulsion. As Parsons' health declined, honours accumulated, knighthoods, medals, scientific awards. But the recognition only confirmed what the world already knew. Modern civilization had absorbed his ideas so completely that it often forgot where they came from. Unlike other inventors whose fame overshadowed their creations, Parsons experienced the opposite. His machines became so fundamental, so ubiquitous, that many forgot to trace the lines back to the man who drew them. When he died in 1931 aboard a cruise ship returning from the Caribbean, the world paused only briefly. The newspapers acknowledged his passing. Engineering societies praised his contributions. But within weeks, life continued at turbine speed. His legacy did not exist in headlines. It existed in power stations humming across continents, in ships cutting ocean waves, in the infrastructure of nations preparing for a conflict even more devastating than the last. The world he left behind was faster, louder, and more dependent on high-speed rotation than ever before. Parsons never witnessed the Second World War, but his turbines did. They powered the destroyers escorting convoys across the Atlantic. They drove the carriers launching aircraft into the Pacific. They provided the electricity for factories producing the machinery of war. His invention, designed in curiosity and refined in obsession, became one of the defining technologies of the modern era. And as his turbines continued to spin long after his death, a question remained unanswered, lingering like the hum of a generator deep inside a warship hull. Did Charles Parsons truly foresee the world he unleashed? Or did his machines accelerate humanity faster than it could ever control? Long after Sir Charles Parsons was gone, the world he helped create continued accelerating. Nations rebuilt after war, industries expanded, and global power increasingly depended on speed, electricity, and mechanical endurance, all driven by turbines shaped by Parsons' original vision. His machines did not fade with time. They grew, multiplied, and evolved until they became the silent heart of modern civilization. If the 19th century belonged to steam engines, the 20th, and now the 21st, belonged to turbines. As the Cold War emerged, nations raced not just for weapons but for energy. Cities swelled, factories demanded uninterrupted electricity. Military bases required constant power. Every corner of society relied on grids fed by massive turbine generators. These machines, some weighing hundreds of tons, operated day and night, their rotations steady and relentless. Engineers understood that the stability of entire countries rested on turbines, whose ancestry traced directly to Parsons' first prototype. Even nuclear power stations used turbines, converting steam from reactors into electrical force. The technology had expanded far beyond anything the Victorian world imagined, but at its core, the principle remained unmistakably Parsons. In naval warfare, his influence became even more profound. During World War II, the fastest and most advanced fleets depended entirely on turbine propulsion. Destroyers guarding convoys across the Atlantic, cruisers patrolling the Mediterranean, carriers launching aircraft into the Pacific. Every one of them relied on turbines for speed, endurance, and strategic mobility. The turbine didn't fire rounds or drop bombs, but it enabled the movements that determined victory. Even today, modern warships, from nuclear submarines to advanced guided missile destroyers, still rely on high-efficiency turbine systems refined across generations. Parsons' invention became not just a tool of naval power, but its foundation. The aviation world also inherited his legacy. When engineers in the mid-20th century began pursuing jet propulsion, they built upon the same basic logic Parsons had pioneered. Compress, ignite, rotate. Gas turbines allowed aircraft to break speed barriers, cross oceans, and eventually reach altitudes and velocities once reserved for science fiction. Every modern jet engine owes part of its existence to the mechanical architecture Parsons introduced. A structure of staged blades, rotational efficiency, and controlled energy flow. His insights expanded from ships to skies, turning turbines into the engines of global movement. Yet the evolution didn't stop there. As industries modernized, turbines entered the heart of energy production across the world. Hydroelectric dams used turbine systems to convert water flow into electricity. Geothermal plants used steam turbines to harness energy from beneath the Earth's crust. Even wind turbines, though vastly different in design, reflect a core principle Parsons understood deeply: rotation is power. The transformation of natural force into continuous rotation became the defining mechanism of the modern world. Despite this unprecedented impact, Parsons remained less known than the technologies he created. History often celebrates inventors whose fame eclipsed their work, yet Parsons represents the opposite: an inventor whose work eclipsed his fame. This anonymity wasn't due to oversight, but to the scale of his invention's integration. The turbine became so essential, so widespread, so fundamentally embedded in daily life that most people never question its origin. They hear the hum of a generator, the whine of a jet engine, the vibration of a power plant, and assume these sounds always existed. But each one can be traced to a small prototype built in 1884 by a man chasing efficiency rather than recognition. As decades passed, the world confronted new challenges: environmental pressures, energy demands, technological leaps, and turbines adapted to each one. Engineers refined blade shapes using computer modelling. New alloys resisted heat unimaginable in Parsons' era. Advanced coatings reduced friction and increased lifespan. Combined cycle plants paired gas and steam turbines for unprecedented output. Even spacecraft used turbine-based systems to drive pumps feeding rocket engines. Parsons' invention had become a universal mechanical language spoken across industries, continents, and technologies. Today, more than a century after his breakthrough, the world still runs on turbines. They power everything from megacities to remote military bases, from aircraft carriers to commercial jets, from national grids to experimental energy systems. Turbines remain the quiet engines behind global civilization, each rotation a reminder that one man's vision reshaped the mechanical destiny of nations. Yet Parsons' story raises a final question, one that extends beyond engineering, beyond history, beyond war. He believed in progress, in the pursuit of speed, in the refinement of machines. But progress is never neutral. Speed alters strategy. Power reshapes politics. Technology changes the balance between peace and conflict. Parsons unlocked energy on a scale the world had never seen, and that energy reshaped humanity's trajectory. Whether for cities, fleets, or industries, his machines turned faster and faster, pushing civilization into an age defined by acceleration. And as the turbines continue to spin, in warships, in power plants, in aircraft cutting across the sky, one question remains: did Sir Charles Parsons give humanity the engine it needed, or the speed it was never meant to handle?